All right, so MAC 248 production procedures. This is the last day of material introduction, and we have 2 more classes next week, and then the course is completed. So what we talked about today was statistical process control, and I just wanted to give a nice high-level introduction to the idea. We've said many times that in order for us to make our processes better, we need measurements. And the measurements give us data. And the more data we can get, the better our measurements are going to be. It's because if you make a whole bunch of measurements, then they end up with you end up with a good average number, but then you also know how much your deviation number is. Sigma, like 6 sigma, or standard deviation, is an extremely useful number that is derived by statistical process control methods, and we need SPC badly. If we had time to teach it, it would be really good. But it's usually a part. Understanding standard deviation is usually part of a semester-long statistics course. So what we just illustrate what process variation is and explain how to measure it. Businesses use this so that their processes and their services and their delivery of whatever that they are giving to businesses and people, their processes are stable, their processes are consistent and predictable, so they can ensure the quality to the people, and they keep their complaints down. If their quality is high, they maintain the perception of quality in their product. Therefore, they get paid a lot better for it. Control charts is how we use that. I gave an example here of a tool wear application that as the tool wears out, we then change the tool. We go back to our wear offset and try to get our process back in the middle of the bands. And then as we do the production run, the tool starts wearing, and we start coming up to being a bigger diameter that will be outside of our tolerance limits, and do the process all over again of changing the insert. So this is a good idea by keeping it in the bands, and then over time we get a standard deviation. We get an idea of how long a tool lasts on average. We ensure that we don't ship any bad parts, and that's why it's done. Rather than checking every single part, which would be prohibitively expensive anyway, we can check every 5th part and ensure that we are within process specifications. So there are 2 causes that we have to look out for: common cause variation, or also just common variation, is something you really can do nothing about. It's like if you're making hamburgers one after the other, and the pickle's out on the edge of the hamburger as opposed to right in the middle of it. No big deal. The customer's not going to be mad because the pickle's off center. So you live with that. You expect it. It's assumed, so it's no big deal. However, special cause variation, and this might be on the test, needs to be addressed. Special cause variation is also called assignable variation, which is deviation in the output that can be clearly identified. Like, oh my goodness, now there are 10 pickles on my hamburger. So it can be clearly identified, and because you can clearly identify it, you can manage it. There's no need to manage the other thing, it's just common cause. These other things, though, if we're putting 10 pickles on a hamburger all of a sudden, our customers are probably not going to be happy about it. So this can be applied to logistics, manufacturing, and service processes, and there are some really good examples on page 213 about it. Then I moved on to a more detailed example, nuts and bolts example of a bearing, and how many standard deviations we want these process limits to be apart. And a lot of times the sigma deviations, these are fiercely contested, because it is so important to not ship a bad product a lot of effort goes into it. There's on page 216 is a whole bunch of good detail about that. If you ever find yourself involved in the quality aspects of the manufacturing plant that you're working in, or you're responsible for that kind of thing, you should remember how to figure out where to go to learn how to figure standard deviation out, and then also how you set those process limits so that your tolerances on the part are reasonable and will do no harm to either your output or to the quality of your part. You know, that's a thing that can be managed. You know, nothing is going to be perfect all the time, and trying to aim for perfection is a pointless activity. You shouldn't even use the word perfect, in my opinion, in the machine shop. It's bad luck. So we can put that to bed now. Next Tuesday we'll have a detailed review for the test that we're going to have next Thursday. We then discussed the paper for a little while, and I wanted to make sure everybody knew what was required on the paper. If you're a good paper writer, then and you generally satisfy the requirements of this paper that I handed out to everybody, write a detailed report that describes the complete production process and relieves or minimizes the constraints or bottlenecks, not eliminates the constraints or bottlenecks, but minimizes, relieves, or manages them with a bias for small, easily accomplished changes and improvements. You can either, if you're a real good paper writer, you can freelance it and satisfy that and teach me something. I'm not gonna penalize you anything for that. I'm here to learn, and I learn a lot of things from my students. Perhaps the more straightforward and easier way to write this paper would be to do that same thing using a 5-step process like DMAIC from Six Sigma, the 5 focusing steps of the theory of constraints, and then the 5 project management life cycles. Define all 5 of the steps, and then start each paragraph with that step and then what happened. At the end of the paper, please give me a good closing to show lessons learned by you and anybody else that may have been involved in that. Thank you, and we'll see you Tuesday.